This is Mrs. O'Neill for AP Chemistry, Chapter 16, Section 3, the autoionization of water. In this section, you will learn that the autoionization of water produces H3O+, that hydronium ion, and OH-. You're going to also understand that the Kw, or the equilibrium constant for water, is H3O+ times OH-. Now think about this for a minute. H2O reacts with H2O to produce the hydronium ion and the OH- ion. So why is it that water is not part of this equilibrium constant? Hopefully it comes to mind. Water is a liquid. And remember, solids and liquids are never part of an equilibrium constant expression. So here's our reaction. Water reacts with water. How can this be? I'm not quite sure, but it happens. So scientists, chemists, have figured out that one of the waters is going to be an acid and donate its H+ to another water. And so now we have these H3O+ and our OH- running around in solution, as well as, of course, some water. So that is the reaction that happens. So pause the video, fill in the notes, and play to hear my words. So I just talked about this. Remember that water is in equilibrium. It makes H+ and OH-. So here's our Kc, or our Kw, they like to call it, for the reaction of water. And we remember liquids are not part of the equation. And we just said that. So the ion product of water, or the equilibrium constant, is just designated as Kw. So we can have the K of lots of things. You already saw Kc, which is just basically an equilibrium constant for general equilibrium reactions. You're going to see Kas for the weak acid, Kbs for the weak bases, and a Kw for water. Also, later on in the future, you're going to see what's called Ksp, which is a solubility equilibrium constant. When we talk about how we're going to come back to that solubility information and think about how those solids, right, break apart into ions, but then those ions can crystallize back into that solid. So that's going to be another equilibrium constant expression. So the the ion product of water, here it goes. This is also on your reference sheet, which is nice. Just again, one less thing to have to memorize. It's right there as a constant reminder. But we can also say that that Kc is still Kw, and that equals 1 times 10 to the negative 14 at 25 degrees Celsius, right? STP. Now, the reason why we want to talk about that, or I'm sorry, it's not STP, right? It is room temperature. 25 degrees Celsius basically is room temperature. So we want to remember that our equilibrium constants are temperature dependent. So I do have to tell you that it's at 25 degrees. This is equal to this value. So therefore, if we kind of rearrange, we can get that pure water is going to be H+ equals our OH. So then each of those H+ and each of those OH- are going to have a concentration of 1 times 10 to the negative 7. That's going to be interesting, and we're going to talk about pH later, but that should be interesting for you to think about how the pH scale is 0 to 14, and our neutral, right, our water solution right in the middle would be a pH of 7. So that's going to be important later on. So a neutral solution. Oh, sorry, hopefully you got that, neutral solution. So there are 3 possibilities. If they equal each other, you have a neutral solution. If you have the hydrogen or the hydronium ion greater than the hydroxide ion in solution, it's going to be an acidic solution. And if you have that the opposite way, where your hydroxide ions are more concentrated than your H+, you have a basic solution. So hopefully that makes sense to you. And again, if we look at these acid-base solutions, that should remind you of that Arrhenius acid-base definition, just dealing with the H+ and the OH-. So let's look at this example. If OH- is 3 times 10 to the negative 9 molarity, I want to know, is this solution acidic, basic, or neutral? So we're going to use our Kw expression, which equals 1 times 10 to the negative 14, equals the concentration of both of them, again, multiplied. We're going to rearrange, kind of plug and chug, and we get H plus equals 3.3 times 10 to the negative 6. Well, what does that tell us? That tells us that our H pluses are greater than our OH minuses, and we have an acidic solution. So remember, when we're in the negatives, right, your negative 6 is bigger than your negative 9. So give it a try. Pause the video and see if you come up with the correct answer. Hopefully that makes sense to you, right? So H plus having a negative 12 is going to be a lot smaller than the 1.0 times 10 to the negative 2, if you want to rearrange this into scientific notation. So your OH minus is greater, so it's going to be a basic solution. See you in class.